Okay, Professor Deskins here, and I have a little handout sheet that goes over units and dimensional analysis. And so I put together this video for you to watch and learn about this. This is really just a review. Almost everything I'm going to talk about today in this video you should already know. Things that you picked up in chemistry classes, physics classes, or maybe some of your introductory engineering classes or whatnot. But really we're going to talk about units and dimensional analysis. Let me just start off and mention and emphasize this, that a number without units is not a number. So in engineering, everything has to have a number. If you don't want units, go take a math course. But if you want to be an engineer, you need to pay attention to units, because oftentimes when we're multiplying units or multiplying numbers or adding numbers or whatnot, if we have the wrong units, it's just going to send out the whole entire problem. It's going to mess up the whole entire problem, and you're going to get a wrong answer, wrong units, and the end result is just going to be garbage. So always write out your units when you write out a number. If you just get in a habit now, you're just going to save yourself a lot of headache going into the future. As your future engineer, career as an engineer, you just need to pay attention to the units and always write them down. So unit systems, basically there's two systems: the international, the SI unit system, which is meters and joules and liters and so forth. This is the system that we tend to use in the scientific world. So you'll see it, we'll use it, and you'll see it pop up a lot. But there's also the English system, which is probably more common in the engineering world as opposed to the scientific world. You're more likely to see English units in engineering than you would say in a chemistry class or a physics class. But English units also are important, and many engineers use English units. So you need to be familiar with them and just be able to distinguish between the two. So let's first talk about temperature. So temperature, common temperature scales that you're used to are Celsius and Fahrenheit. And 100 degrees Celsius is equal to 212 degrees Fahrenheit. 0 degrees, forgot my C there, Celsius is equal to 32 degrees Fahrenheit. Those are the temperatures at which water boils and the temperature at which water freezes. And we have these nice little formulas that allow us to convert between Fahrenheit and Celsius. So all of you should be familiar with Celsius and Fahrenheit and be able to convert them using the formula here. You should also be familiar with the Kelvin scale, and maybe to a lesser degree the Rankine scale. So in degrees, the Celsius and Fahrenheit scales, you can have negative temperatures. The Kelvin and Rankine scales have been developed so there are no negative temperatures. The lowest you can go is 0. And the way that you convert between Celsius and Kelvin and Rankine and Fahrenheit is simply adding in a number, according to those two equations there. So if I have the temperature in Fahrenheit, I can just add in 459.67 and I'll get the degrees in Rankine. And it's impossible to have a negative value in the Rankine scale. Same thing with the Kelvin scale. And oftentimes when we're dealing with energy and thermodynamics, we need to have our values in our temperatures in the absolute scale, Kelvin or Rankine, in order to do our calculations. Next units we have here are pressure. And again, these should be pretty familiar with. You should be familiar with these. There are various units we may encounter: the bar, the atmosphere, milligrams of mercury, also known as torr, psi. Common unit is atmosphere, which usually around the pressure of a typical location is around 1 atmosphere. So it varies from the elevation, the weather, and so forth. But if I were to go outside today, it's probably be about 1 atmosphere. So that's a pretty common unit. Let me mention gauge pressure versus absolute. So sometimes you may see a pressure given as gauge temperature. So gauge pressure simply means that it's the absolute pressure subtracting the atmospheric pressure. So it's not the correct pressure, but it's a difference between the two, the absolute and the atmospheric pressure. So if the atmospheric pressure is 1.01 atmospheres and the absolute pressure is 300 atmospheres, the difference between those two would be the gauge pressure. And same thing, we can convert between absolute and gauge and by knowing the atmospheric pressure. And the reason why this is because why we have gauge pressure is that many pressure meters are designed, they're simply designed to measure the difference between pressure of the atmosphere and the pressure of whatever's being measured, of the fluid or whatever. So oftentimes when you have some sort of pressure device that gives you the pressure, it will give it to you in gauge pressure. And so you just have to simply take that gauge pressure and convert it to the absolute pressure according to the equation there. We have units of volume, meters cubed, liters, gallons, feet cubed, centimeter cubed, etc. Don't think I need to say anything much on those. Let's talk about stuff, the amount of stuff. That's what I generally call when we're talking about how much stuff we have. So mass, I think, should be pretty intuitive to you. We have grams, kilograms, pounds mass, which is our units for the English system, and then we might have tons, and I'm sure there's other units of mass. If you look in your textbook, you'll see a list, and if you Google, you'll find more units of mass. But basically, that's how much material we have. The other unit that we deal with when we're talking about how much stuff we have are moles. And you should be familiar with moles from your chemistry class. There's just one thing that you may not have encountered that I'll mention here, which is the concept of English moles and SI unit moles. So when we talk about moles in chemistry, we're talking about SI moles. So SI mole is 6.02 times 10 to the 23rd atoms or molecules. So that's the number you've probably seen before, mentioned it in some of your chemistry classes. It's Avogadro's number. So 1 mole or a gram mole is equal to this. And when I say gram mole, I'll get to a little bit why we call it a gram mole. But often when we talk about moles, we're always 99% talking about SI moles or a gram mole. It's called a gram mole, but we just shorten it to call it a mole in your chemistry courses and in everyday life. There's an alternative type of mole, which is known as the pound mole, and a pound mole is equal to 453.59 moles, or 453.59 gram moles. So if I wanted to know how many atoms or molecules were in a pound mole, I'd take 453.59, multiply it by 6.02 times 10 to the 23rd atoms or molecules. So the pound mole is just simply the type of mole system that we use in English units. The mole or gram mole, as its proper name is just the type of moles that we use in SI units. So again, SI units we use moles or gram moles. The full name is the gram mole. English units we use pound moles. Pound moles, honestly, we don't encounter them that often. They don't come up often at all, but you should be familiar with them in case you do encounter them at some time in your engineering career. Molecular weight. So molecular weight is how we convert between mass and moles. And the molecular weight, we can look on our periodic table and add up the appropriate numbers to get the molecular weight of some molecule. A molecular weight of 12 would indicate that we have 12 grams per gram mole, or, as we often write it in chemistry or in our courses, 12 grams per mole. Again, we just shorten gram mole to mole. So 12 grams per mole. Or it could mean 12 kilograms per kilogram mole, where a kilogram mole is reference to a kilogram. Or it could mean 12 pounds mass per pound mole. So this would be the English units definition of the molecular weight, where we're taking into account the pound moles, English units for moles, which is the pound mole. And again, this definition right here is the one you've probably seen before. It's the one we use most often, but molecular weight can also be used in other unit systems. Mass and mole fractions. The mole fraction is simply the number of moles divided by the total number of moles. So the mole fraction of A in this example is just 12 divided by 20, so we have 20 moles total. 12 moles of species A gives us a mole fraction of 0.6. And then let me just write this out here. The sum of xi is equal to 1. So if we were to add up all of the mole fractions in a solution or some sort of mixture, the total number of mole fractions, if I add them all up, has to equal 1. Same here with weight fractions. The mass fractions, the weight fractions or mass fractions, it has to equal to 1. And then mass fraction is simply just the mass of species A divided by the total mass. So it should be, again, review from your courses that you've already had. Okay, let's go to the next page. Let me just briefly mention energy. I'm not going to say much about them other than there are various units for energy. Most often we use joules in SI system, but there are other units. We'll see kilojoules, which is an SI unit also, with just the kilo prefix added. But there's BTUs. That's a common unit in engineering. Calories is another unit of energy that may pop up. But again, you should be familiar with those. Lastly, let me talk about dimensional analysis. So dimensional analysis is just basically paying attention to your units and writing out a solution so that all the units cancel out properly and you end up with the answer with the correct units. Again, got to pay attention to units or you're going to get totally wrong answer in the end. And especially when you're taking tests, you're doing homeworks or whatnot, I like to give you partial credit. If you get it wrong, I'd love to give you partial credit, but if I can't understand what you're doing and you're just writing down random numbers and I can't tell what you're doing, I'm not going to give you as much credit. But if I can see where you're coming from and I can see, oh, this is your temperature that you used and why you use this temperature, and I can follow your basic solution, even if it's wrong, I'm more likely to give you some partial credit. So even if you do it right and you don't write it out correctly and you don't follow the procedure right, you still might not get full credit, even if you get the right answer in the end. It's just so important to write out a correct solution where you pay attention to dimensions or units. So at this point, I'm just going to solve this problem right here and write out my solution, how I would go about solving it. If you want to go ahead and solve it yourself, and then you can go ahead and compare your solution with mine, go ahead and stop this video right now and then go solve it yourself and then come back and look at my answer and see how it compares with yours. But if not, you're just being lazy and you don't want to do it. Just keep watching the video. So anyways, so we have this simple example, PV equals nRT, basic chemistry example. We're given some information here, the pressure, the temperature, the volume, and we're asked to, and we're also given the R value, which we could look up in our book, our Felder or So book, or Google it or whatnot, but we're asked to find the number of moles. So to do this problem, we're going to have to pay close attention to our units and make sure everything turns out just right. So let me go ahead and start this. So first thing I want to do is I want to start out with getting the temperature in the proper units. And why I say this is because temperature, when you're using PV equals nRT, has to be in the absolute temperature scale. Celsius is not absolute temperature, so we need to take our Celsius and convert it to Kelvin, because Kelvin is the correct units, absolute temperature units for this problem. And you notice also here's a K, so that tells us that we're going to have some cancellation here where K is taken into account. If I look on my previous page, I can look at the formula for temperature, and temperature is simply equal to 333 degrees Celsius plus 273.15, and so temperature is equal to 606.15 Kelvin. So that's our temperature. Pretty straightforward. We just use the formula from the previous page that I showed you, which you could also have found in the book, and we got that. We have the formula up here for PV equals nRT. We can rearrange that. N is equal to PV over RT. So we just did some simple rearrangement. So let's look at here how we would go that. Let me just scroll this up. Let me just write out my solution. N is equal to, what's the pressure? 1.3 bar. And I like to write these in little parentheses. It helps me to keep them, things separated. Volume, 2.3 gallon. And then we have to have a conversion between liters and gallons because our R value has liters, and that's 1,000 liters divided by 264.17 gallon. And I just looked that up. You can look up the conversion factors. Again, they're in your book, your Felder-Rousseau book, and probably the other books too. You can Google it. It's not hard to get these. And I'm running out of space here on this particular line, so I'm just going to put a little multiplication here because I'm not going to be able to fit all these numbers here. But we need to divide by R, and this is where I need to pay attention. Write out my units there. 0.08314 liters times bar. So that's my R. I was dividing by R, so the value is on the bottom. And then I'm going to divide by temperature, 606.15 Kelvin. And if I go ahead and do this, let's check the units. Gallons cancel. Liters cancel. Kelvin cancel. Bar cancel. Voila. Good. We're left with mole of our only units left. So that's a real good sign. That means we're on the right path. And if I do the math out right, that comes out to 0.22 mole. And I think I'm happy with that. I'll go ahead and circle it because I think it's a good answer. And that's basically it. That's how we go about paying attention to our units, doing our dimensional analysis, making everything turns out okay. So again, just a review from what you've hopefully learned in your previous classes. So thanks for watching the video.